Performance analysis of digital moderation schemes considers the power spectral density, the probability of error, bandwidth efficiency, and power consumption. We have already discussed the first two, that is the probability of error and the power spectral density. Now we discuss the bandwidth efficiency and how the choice of different moderation schemes is dependent on how efficient it is in respect to the use of bandwidth available. So what is bandwidth efficiency? It's also called the spectral efficiency and is defined as the ratio of the transmission bitrate to the minimum bandwidth required by a given digital moderation scheme. And it is measured in bits per second per hertz. And it's normally normalized to a 1 hertz bandwidth. And it indicates the number of bits that can be transmitted for each hertz of channel bandwidth. Now, it's often used to compare the performance of different moderation schemes, and we'll see it shortly. But mathematically, bandwidth efficiency is defined as the ratio of bitrate (RB) divided by the channel bandwidth, which gives us a unit of BPS per hertz, where RB is the data rate or bitrate, and B is the channel bandwidth measured in hertz. So we'll now consider that how we can evaluate the bandwidth efficiency of an M-array FSK as well as other multiple array moderation schemes like M-array PSK. We have already met the M-array FSK, M-array PSK, and other moderation schemes like QAM, ASK, among others. And the ones that are multiple signaling schemes are these three, but we are going to start with the first two and find out how efficient are they in terms of spectrum usage, and find out is there one that is better than the other in terms of spectrum efficiency, or are they the same, and how applicable are they in different scenarios, depending on what is the factor that the efficiency depends upon. So first and foremost, we start with FSK, and we know that M-array FSK consists of M orthogonal set of frequency shifted signals. For instance, with BFSK, we know that the binary 1s and binary 0 are transmitted by different frequencies F1 and F2. Therefore, if we have M symbols, then we will have M number of frequencies all the way up to FM. These signals are said to be orthogonal in frequency, and for coherent detection, these or the adjacent signals, say F1 and F2, they must be separated from each other by frequency difference delta F equivalent to the symbol frequency divided by 2. For instance, I want to be clear that the bit rate, when we normally have bit rate and the symbol rate. So in this case, when I say F symbol, in fact, the better phrase to use is not F, but R, which is supposed to mean the symbol rate. So we are saying that if the symbol rate is given by RF, or rather RS, then the difference between F1 and F2 must be equals to or greater than the symbol rate divided by 2. And remember that we can always find the symbol rate in terms of bit rate, where we say that the symbol rate is equals to MRB, where RB is our bit rate, where the small m is given by the logarithm of m to base 2. So what we are saying here is that if we are given a bit rate of say 10 bits per second, and we are using say M-array 8-array PSK or FSK, this 8 is our capital M, and therefore the small m is going to be given by log to base 2 of 8, which is equals to 3, and therefore our symbol rate will be equals to RB divided by 3. And I want to make this correction. This is not supposed to be times. This is supposed to be division. Because how we know the relationship is the symbol period, which we normally refer to as TS, is the one that is given by small m TB. And therefore, if we are talking about the symbol rate, RS is going to be given by RB divided by M. So we were here and we have just said that for the orthogonal sets of signals to be transmitted or detected coherently, the difference between the two frequency symbols must be minimum of symbol rate divided by 2. So we have also said that we know that the TS is given by TB times M, which may be represented as TB log to base 2 of M. We also want to find the required channel bandwidth for us to transmit the FSK signal for an M array FSK, and we can symbolize it as BMFSK. We can be able to evaluate it as M times the difference that we have just seen here. So if we have M symbols and each of them is separated by delta F, and delta F is given by RS over 2, then we need to have M such frequency differences, delta F, for us to set the entire M symbols. And therefore, we are going to say that the bandwidth requirement of MFSK is actually delta M delta F, which is equivalent to M times RS over 2, because we are saying that 1 delta F is equals to symbol rate or half the symbol rate. And we have already seen how we can be able to calculate this RS, and therefore we can say that this may be expressed as M divided by 2. RS is equivalent to the reciprocal of this. And therefore, the reciprocal of this is 1 over MPB. And we had also seen that we can be able to express M as the function of number of symbols capital M, which is log to base 2 of capital M. And therefore, we can still express our bandwidth, channel bandwidth requirement of MFSK as this capital M divided by 2 multiplied by 1 over TB multiplied by 1 over log to base 2 of M. And therefore, the final expression for the bandwidth required to transmit M array FSK may be given by capital M all over 2 TB log of 2M. And again, we can still express the TB in terms of RB, or the bit rate, which is the reciprocal of TB. Therefore, we are going to have capital M RB divided by 2 log to base 2 of M. So that is the bandwidth requirement of MFSK motivation scheme. So our final question is, how do we evaluate the bandwidth efficiency of M array FSK? We don't know M, we don't know the bit rate. How can we evaluate it? We can be able to say that we have already defined efficiency, or the bandwidth efficiency, as the ratio of the bit rate, or the rate at which the binary data stream is arriving, which is RB, divided by the channel bandwidth that is required to transmit the M symbols, which we have already found from here to be given by this equation right here. You can call this one equation 2. So we are putting equation 2 here, so which is MRB, and this what was in the reciprocal, we can put it in a numerator, which is 2 log of 2M. And therefore, if we evaluate this equation, what we will find is that the final expression for the channel, for the bandwidth efficiency of M array FSK, is actually given by 2 log of M to base 2 divided by M. And this serves as the final expression for bandwidth efficiency of M array FSK.